our PicnicDay physics play. Please turn off your cell phones now.
A long, long time ago in a galaxy far, far away. Oh, war strong spirit. Many of you have heard of the great adventure Indiana Jones, but how many of you know of his cousin, Montana Smith? Once upon a time, Indiana Jones invited his cousin on an adventure to a seemingly deserted island. They thought they were looking for a valuable gem to fund his research, but little did they know that on that very island lived the evil wizard Physico. Indiana's strength would prove to be no match against Physico's magic. Only you and the power of physics will help them. Are you ready to save our heroes?
Woo! Yeah!
I sure hope so.
Let's go, Montana. I think we're almost at the diamond. But be careful. We don't want to get attacked by a wild animal.
Uninvited guests I see. I am the evil and magnificent Wizard Physico. And for your trespass into my cave, you two will be my prisoners. Forever. The physics may be theoretical, but the fun is quite real.
Indiana, what are we going to do?
Don't worry, Montana. We got physics on our side. This was just a Tesla coil that he used to trick this wand into looking magical. What happens here is this bottom right here generates electrons. And it runs these electrons up a coil until they get to this magnetic sphere up here. Or not metal, not magnetic. And what they do is all these electrons sit there and they build up and they build up and they generate a high voltage. You probably know that word from like batteries and stuff. So then what happens is these reach such high voltage upon the order of magnitude of 10,000 volts, where it actually ionizes the air and causes those lightning bolts to appear that you were seeing. But what happens when that happens, when it happens then, is all this energy and electrons are up in the air floating around. And so when he holds his light bulb, as all this is, light bulb up, the electrons are able to actually like flow through and complete the circuit and like get the light bulb to actually light up because all the energy's there. Science.
Indeed, Physico is not your ordinary wizard. He uses physics to trick his opponents.
Oh, you think you're so smart because you watched a TV special on organization. How about my testing intelligence?
Indy, I think it's a trap.
Nonsense, Montana. I'm Indiana Jones and you're Montana Smith. Together we can defeat Physico with our eyes closed.
Go ahead, Dr. Jones. My challenge is quite simple. If your metal block can go down your tube faster than mine, you two will be free. In fact, I'll even throw in the diamond.
This is easy. Gravity would say that these two similar looking blocks would go down at the same speed.
That's quite
What's going on here? How could this be?
Poor Indiana Jones is unfamiliar with the physics of Lorentz forces.
Indy, this has to be a magnet. When the magnet goes down the tube, it induces a current. And that current acts like a magnet itself and opposes the motion of your magnet.
Is this because nature doesn't like change in it?
Exactly.
Oh, so when this pipe is before, it has zero magnetic field in it, right? But if we take a magnet and we start passing it through, all of a sudden there's a magnetic field where there wasn't originally. But the pipe doesn't like that at all. So what it is going to do is it's going to induce what's called a Lorentz current. Now I learned about them. It's going to cause a current that creates a magnetic field that opposes the one that's induced into it. So that way its net magnetic field is still zero as it was before.
Nature isn't the only thing that abhors change. So do I. No deal.
Never mind, let's go anyway.
You two can't escape.
Physico, I'll make you a deal.
What kind of deal are you talking about?
If we can't defeat your challenges, we'll do your homework and chores.
That's not about it.
And we'll be physics 7th graders.
No, students.
Montana Smith and Indiana Jones are now trapped in Physico's world of science, where they will have to face minions in duels of physics. The only way they can escape is if they can correctly understand all the principles of physics presented. They will need the audience's help. Enter first challenger.
Look, it's the first minion, grad student.
Are you the first minion?
Oh no. Don't tell me you're here for a fate-determining physics challenge. You are. Physical always schedules these during my lunch break. Let me guess. You wagered you'd be physics 7 graders.
Maybe.
That's how he got me. You won't kill me if you know that I have a challenge ready for you. I have a plan. I'll be right back. A physicist's best friend, Pickles. I'll have your challenge ready in post-haste. And some of these, and some of these. It's perfect. An ordinary pickle hooked up to 2 nails, which are attached to 2 wires attached to this cord and to this plug. When I stick this plug into an electrical outlet, these nails will be electrified and charged with electricity. What do you think will happen?
What do you guys think is going to happen?
Well, heck if I know. Bombs away. As you can see, the pickle is flowing.
Not exploding.
All right, Indiana Jones and Montana Smith, if you can explain to me why this pickle started glowing, you will have defeated the challenge.
I got this. This pickle has salt in it, and that salt acts as a conductor. When you plug both of those wires in, it's conducting the electricity all the way around through the circuit. Plus, those sodium atoms, they absorb electricity, and when they let off all that energy, they let it off in the form of photons, or light. But, Mr. Minion, this doesn't just work with pickles. I'm going to need some volunteers from the audience. Anyone else need one more? Here. All right. What I have here is a speaker. And this speaker has 2 wires on it that aren't touching. They're not connected at all. What I'm going to do is I'm going to hold both ends of this, and you can hear it. Can you hear it? It's making a sound. All right, and when I let go, it stops. So what we're going to do is we're going to try to do this all together. So I'm going to hold your hand on this side, and you're going to hold his hand there, and you're going to hold that end of the wire. Can you guys hear that? Yeah. There we go. And now let go. It's going to stop.
Woo!
Is in essence just exactly like a wire. All a wire is this, it's an electrical conductor, which just means that electrons are able to pass through it very easily. And you, as a human, have a lot of electrolytes. I'm sure you've heard that word. All those are just very conductive elements and stuff. So when electrons are trying to pass through, they can, because you have a lot of electrolytes in you, and you are a conductor because of those. So that's what happens when the electrons are going out from one end of the speaker. They go through the wire, they're able to conduct along all your electrolytes, and then through each other, and then back through the other side of the circuit, and then they make the noise.
All right, Indiana Jones and Montana Smith, you've defeated me, and you've thoroughly proven you understand electromagnetism. But there are more challenges to come. I'm going to go sulk in the basement.
Hope there's not many more of these challenges, Montana.
Don't worry, we got the power of physics on our side.
Hi. Hello, you guys. Oh, wait, yeah, you guys are the intruders, right? Yes. So I've scheduled for you guys to challenge, right? Alright, so, let's get, oh, here we go. Alright, let's get this one. So, your challenge is to spin someone on this chair using that wheel over there. And you have to correctly explain it, or else you're only going to get half credit.
Another volunteer. Okay, so why don't you take a seat then on this chair over here? And so we're going to get, what we have over here is just a bicycle wheel. And so we're going to get it spinning really fast with just the motor. So what we're going to do is we're going to give you this, we're going to give this spoon, you're just going to hold on to it like this. Okay, so grab onto it, and then turn it. Whoa! Hey, so that's what's up. Cool, thank you very much.
Woo!
Because of something that it has to do with conservation of angular momentum, doesn't it, Montana?
It does exactly. When he sat down on that little spinning chair thing, he had 0 angular momentum. Angular momentum is just the physics of spinning stuff. So when he sat down, he wasn't spinning at all, but we handed him a spinning wheel. When he turned it, he changed the direction of that angular momentum. So that means that chair has to turn in a way that will counteract that, because, like you said, nature hates change.
And momentum is one of those things that just is conserved in nature. In the same way that energy is, or like linear momentum, so just go straight. Angular momentum is also conserved. Especially when we gave him the wheel that was spinning, the angular momentum was actually pointing horizontally. So he had 0 momentum in the up and down direction, is how you can think of it. But when he turned the wheel, the angular momentum actually went from being horizontal to actually vertical. So now there was angular momentum up in the up direction. But the chair has to then spin to counteract and apply downward angular momentum to oppose that. So that way it's still 0. So that's why the chair has to spin.
Thanks, y'all got 100% on this. Well, I gotta go back to okay, so you're gonna have some more challenges and some more physics fun. So I'm gonna bid you guys peace.
I guess it's my turn now. So, I have here a sign. Your challenge, read the sign. I'll help you with a light.
Okay, so you guys all have your 3D glasses on, so if you close an eye and then tilt your head a little bit to the side, and then now tilt it the other way. Whoa! Science, cool. Yeah, it's kind of cool to have it there. So share, feel free to share. What are the equations that you guys are seeing? But Montana, how is this working?
This works because one of these equations is letting the light become polarized up and down. That means all the light waves are traveling in up and down motion. And the other equation is letting all the light waves traveling in a side-to-side motion. That means they're perpendicular. When you cover one eye and tilt your head, it's going to let one of the equations through. It's going to let the one that's going like this one sit, like this direction. And when you turn it the other way, it's going to let this one through. That's why when you turn your head, you can see both.
You know, I wish we were in.
Oh, yeah, I'm getting sick of all these videos too.
Unfortunately, there's more. So, behind this wonderful sign, I have a candle. Yeah, suppress the moving eyes. But this isn't just any candle. NASA recruited physicists to make a candle that wouldn't go out even when lit. I'll demonstrate. I have here a glass of water. I have my candle. I'm going to pour water on the candle. The candle didn't go out. So maybe I just didn't pour enough on. pour a little bit more. Pour a little bit more water on. Can you believe it? The candle didn't go out. Now maybe you're thinking, well, this is like one of those happy birthday candles that can blow on forever. It still comes back. So I'm going to fill the entire container with water, just to prove just how awesome this candle is.
Turn light, we can't see.
More light! It's still on. Can't see it. Well, can you see it? Can you see it? Yeah. Oh, perfect. Okay. Well, good. Explain that.
Okay. You're just using trickery of optics. The real candle isn't behind the glass, but actually here. What's happening is that this glass panel right here is it's actually taking this image of this flame and it's projecting it back onto this candle that's right over here. So it just merely looks like the flame is on the candle in the back when it's actually was on the one here. So obviously when he puts water on the one in the back, it's not going to do anything to that one. So it still looks like.
Rats, you win again.
Montana and Indiana have finally defeated all the physical minions, and now hopefully the evil wizard will let them go.
Physico, we have defeated all your challenges. Now let us leave.
I'm a genius, not honorable, no.
Physico, I'm going to challenge you.
So bold, go ahead.
What I have here is I have a giant bank of capacitors. Right now I'm charging them all up with a bunch of electricity. I have it plugged into the wall down here. I am filling these capacitors with a bunch of energy, lots of electrons, just like they really want to get out of here. What do you guys think is going to happen when I try to run this tiny little wire right here?
Explode.
Think about it like you have a big giant river, like say the Amazon, and you try to fit it all through like a tiny little pipe. What would happen? It would be very hard to get all the things to fit through there. And now consider the fact that these are electrons. So electrons are all negatively charged, which means they repel each other, right? They don't want to be nearby each other. Well, we're gonna do it. You'll see what happens. If we flip it to the light switch, you're exactly right. But we're gonna try to fit it through a little tiny little wire first to see what happens. So these electrons are all like wanting to repel. So you're already taking all these electrons that have this energy, and then you're forcing them to be really close to each other when they don't really want to be. So something cool is gonna happen. Last time it didn't like charge very well, so we're gonna kill a little bit more time. So it's joke time. Okay, so Einstein, Newton, and Pascal are all playing hide and go seek. And they choose Einstein to be it. And so he starts counting, they're like, Einstein, don't count to 100. And so Einstein goes in the corner, he's like counting 1, 2, 3, counting away. And Pascal goes and he hides in the closet. And he's hiding super well, like, ain't no one gonna find him. And Newton's a little rascal, and he goes and he just stands, stands like right there. Newton just stands right here, and he just draws a little square box around it. And he just stands there. And this is good. Then Einstein stops counting, he turns around and he's like, Newton, I found you. And he's like, no you didn't. You found Pascal. Okay, this is why. Because a Pascal is just a Newton per square meter.
Rah, 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 rah.
Alright, so I'm now going to try to put all of this stuff through this little tiny wire. I'm going to unplug it even so you guys see that I'm not cheating. Alright, I'm going to get a countdown from 3. This is pretty exciting. Alright, everyone. 3,
2, 1.
I got another joke. So they're driving along, and Heisenberg's a little bit of a speed demon. He's going, and a cop pulls him over. There's the lights on and pulls him over. And so the cop goes up to the window, and Heisenberg's in the driver's seat. And the cop looks at him and he says, "Sir, do you know how fast you were going?" And Heisenberg says, "No, but I can tell you exactly where I was." So then the cop says, "Sir, I'm going to have to search your car." And they're like, "Oh, okay, go ahead." And so the cop says, "Okay, I'm going to open up your trunk." And he goes in the back and he opens up the trunk and he finds a dead cat. And he says, "Hey, do you guys know you have a dead cat back here?" And Schrodinger says, "Well, now I do." So Heisenberg's a pretty famous physicist. He's not just from Breaking Bad. So he was one of the founders of quantum theory, and what he came up with was this notion that it's in the quantum level, which is just really tiny, small things. It's impossible to know both the momentum, or you can think of it as the velocity of a particle, and its position very well. And so it's a trade-off. So if you know the velocity really well, you lose uncertainty in the position, and vice versa. That's why it's funny when he says no, but I can tell you. So let's hope this works.
3, 2, 1. Wait.
Why was the Schrodinger funny? That's a good question. I got a good answer. Okay, so Schrodinger was also a well-known physicist who was